Hello, everyone. So sorry I couldn't meet live with you today. Just wanted to help you finish up your work for Thursday. So remember, at this point, you should have already watched the Lesson 2 launch video and attempted to start the task for Lesson 2 in your workbook on your own. You can use this GeoGebra activity that is linked to graph the triangles and let GeoGebra do the rotations for you. And then you should have already submitted a picture of experiment 2, which is page 10 in your workbook, by adding that file to this assignment in Google Classroom. If you have done all of that, you are ready to watch this video, and I will help you summarize the rest of Lesson 2 and all of our properties of rotations. Alright, so I have moved to page 11, which is the last page of this task in your workbook, and we are going to talk through experiment 4 together, and then, like I said, wrap up those properties of rotations. So question 1 that you should be answering for each experiment: what is the slope of the line segment AB? Okay, good. The slope of this line segment is going to be negative 3 over 2. You can see from point B, if you were to count down 1, 2, 3, and to the right 2, 1, 2, that is how we can find the slope of the graph. Excellent. Question 2. Where could you put point C? Remember, there are two options, but only one of these will be correct. Okay, good. Point C could be at the point 2, 6. The other place you could have located point C would be at 0, 3, right here to create a right triangle. Then the next question, 3, is, well, how do you know for sure that if I were to connect these line segments that I would have a right triangle? Okay, good. Within this task, we should have discovered and learned that right angles are definitely made up of, let's watch it happen, horizontal, yep, and vertical lines. So anytime in the coordinate plane when you have that horizontal and vertical connected, it is going to connect at a 90-degree angle. All right then. So let's fill in that triangle and actually work on the rotation. Have you graphed it yet on your graph paper? Are you going to use that patty paper or tracing paper, or have you used GeoGebra maybe to support you? All right, well, here's what it looks like. All right. And then that question 4 is asking us, how do we know that triangle A prime B prime C prime, and that just means that it's the image triangle now, has been rotated 90 degrees? All right, and since the answer was on your screen already, that was an easy one. We know that this B prime C prime, let's watch it happen, yeah, went from being horizontal when we answered in question 3 to vertical now in question 4. So it went from horizontal to vertical, which we know makes a 90-degree angle, which is now associated with that 90-degree rotation. All right, so let's check out C prime A prime. Yeah, cool. So C prime A prime, again on that new triangle or that image triangle, is horizontal, but it used to be vertical. You can kind of see where these green lines intersect right here at the center of rotation point A. We are creating that nice 90-degree angle for our 90-degree rotation. Okay, awesome. So what is the slope of this new hypotenuse? That's question 5. Okay, good. The slope of this hypotenuse is 2/3. So you could rise 2, so up 2, and then run 3, 1, 2, 3, to get the new slope. And every experiment is asking you, what do you notice about these slopes? So this is actually one of our properties of 90-degree rotations that I want to solidify today. The summarizing question in your notebook says, based on experiments 1 through 4, state an observation about the slopes of perpendicular lines. Now you should already know from Math 1 that perpendicular lines will always have opposite reciprocal slopes. So remember from experiment 4, those slopes were -3/2 and 2/3. So -3/2 is opposite from 2/3, which means that one is negative and the other is positive, and they are reciprocals, which just means that the fraction has been flipped upside down. This is a property of 90-degree rotations. Anytime you connect the pre-image point, so maybe we're looking at point C in that pre-image, to the center of rotation, which would be A, and then the image point, which would now be C prime, that is going to make a right angle. We saw that with the vertical and horizontal lines that are green, but we can also see that with the hypotenuses. Watch that dotted line. And so those two slopes also create a 90-degree angle when you connect them, which helps us notice that this has been a 90-degree rotation. All right, now that we have been over the task, lesson 2, it's time to revisit our notes on page 4 and make sure that we have the properties of rotation and what we need in order to perform a rotation written down. Now you should have more notes than I do here on translations and reflections. I just wasn't sure exactly how far we were going to get, so I left mine blank for now. But let's go through these rotations specifically. Obviously, since day 1, we know that a rotation is a turn. What do you need in order to perform a rotation? Hopefully that by this point we've already talked about you need to know how many degrees you're rotating. Have you rotated 90 degrees, 180 degrees, 270 degrees? And remember, to make a full circle, you could rotate 360 degrees, but you would be back where you started. Okay? You also need to know which direction are you rotating? And so you have two options. You either rotate the same direction that a clock goes. Sometimes I have to stare at the wall and picture what that clock looks like. So it would kind of go to the right if it was clockwise, and then counterclockwise, like my little arrow here, is actually the normal rotation. And so since our workbook was not specifying which direction we were supposed to be turning, we were supposed to be turning counterclockwise. I know this seems kind of weird for, you would think going the same direction of a clock is normal, but in math, the way you can remember this is to think about the quadrants that you make up when you are graphing something in the coordinate plane. So just a quick sketch. This is quadrant 1, this is quadrant 2, quadrant 3, and quadrant 4. And so actually when we travel from quadrant 1 to quadrant 2 in math, that is considered normal. And so that's counterclockwise, and so when we're rotating, a normal direction would be counterclockwise. Okay, the last thing that we need to know for rotations is what point are you rotating around? And so that's called the center of rotation. And remember, in the task that we were working on, they were always rotating around one of the vertices or one of the points of the triangle, like point A. But you can also rotate around other points. Our lizard that was diving into the mud puddle was rotating around some random point. And then a lot of times we actually rotate around the origin. So when you're using your tracing paper, okay, and I'll just use this as an example, but if we were tracing something, if we wanted to rotate around point A, you would hold that point down with your pen and then perform the rotation. If you were rotating around this random point, whatever that is, you would hold that point down with your pen and rotate around it. Okay, and same with the origin. So if I'm holding down the origin right now, we could rotate around the origin. Okay, awesome. And so then the details of the properties of rotation should be new for us now that we've summarized this task. Okay, we know that all three of these types of transformations are rigid motion. Remember that rigid motion means they do not change shape or size. They will produce congruent images, which means that those images are exactly the same. Obviously, in a rotation, they are oriented differently, which means they've been turned, but they are going to be exactly the same size triangle, and the triangle will still be a right triangle with the same legs and hypotenuse. Okay, so then one of the things that we've noticed, and maybe we haven't pointed it out yet, but anytime we connect those points on the pre-image and the image, they are going to be equidistant from the center of rotation. Okay, so think about the reflections. We should have talked about by now that if you are performing a reflection, a triangle on the right side and the left side of the y-axis, for example, are the same distance from the y-axis. Okay, well, this is true for our rotations, where each individual point will be the same distance from the center of rotation. So it's just one of our properties to help make sure that we have rotated correctly. All right. Another property is for specifically 90 degrees. I'll go ahead and uncover all of those because we've been working with 90 degrees within this task. We have noticed that anytime you have a vertical line, it becomes a horizontal line. That's super helpful anytime you are rotating an object, especially if your object already has a vertical or horizontal line in it that you can keep up with. Okay, also the slopes of any diagonal line within that pre-image are going to become opposite reciprocal slopes in the image. So again, I'm sorry, I don't know if I said that right. If you are looking at the slope of the pre-image, the first shape that you start with, then you would have an opposite reciprocal slope in the image. Okay, and then finally, the one that we talked about at the very end of the PowerPoint is that when you connect, again, those pre-image to the center of rotation to the image, you're going to create that 90-degree angle that we saw with the black dotted lines at the very end of that lesson when we were summarizing. So that's going to be really helpful for you to kind of visually check and see if you have gotten a perfect 90-degree rotation when you are asked to perform one. Now, the one kind of rotation that we might not have looked at a lot so far is a 180-degree rotation. And so a 180-degree rotation has some properties that are similar to 90 degrees, but they have rotated halfway around at this point. So if you think about performing that 90-degree rotation twice, your vertical line became horizontal, but then it went back to vertical again. So actually, any vertical lines are still going to be vertical lines in your image. And that could be said for horizontal as well. So any lines that were already horizontal are still going to be horizontal in your image after a 180-degree rotation. Okay, this last one got abbreviated a little bit, but it is similar to this bullet for 90-degree rotations in that connecting any of those points from the pre-image to the center of rotation to the image is going to actually be collinear. Collinear just means that it's going to make exactly the same line. So we'll look at an example of a 180-degree rotation. All right, so I've turned back to page 10 just to take a look at experiment 3 and add on a triangle that would be a 180-degree rotation. So within the experiment, you've already done these two yellow triangles, which is your 90-degree rotation, but I have added on the 180-degree rotation triangle. So if you think about adding 90 and 90, we would have now traveled 180 degrees. So if our original triangle, this pre-image is the one that was in your book for experiment 3, then we can rotate 180 degrees and land up where this purple triangle is. So the properties that we had noticed really quick were that anytime you had a vertical line like BC, in the image you would still have a vertical line. Or AC is horizontal, and again, you would still have that horizontal A prime C prime. I use the double prime because we've actually moved it twice. We'll talk about that later. Okay, and the collinear part. So if we look at BA, originally that hypotenuse, it actually continues on the same line right here. So collinear, if you connect B to the center of rotation was A, and then A to that B prime on the image triangle. So again, collinear means the same line. And that wraps up our properties of rotations.